Hey guys, welcome. Hope you're having a great weekend. I am. Weather's wonderful right now. This is your second and last video from Chapter 8. If I use this video in future years, I'm not sure if it'll necessarily fall in sequence with where you guys are at this year, but this will be the only video you have to watch during homecoming week, which is good. It'll give you more time to enjoy the week, do things in the evening, and have fun with friends. What we're going to talk about is we're going to look at the linear regression model further, and to do that we're going to start with a refresher on the linear regression model. There are a couple of things that I want to make sure are clear to you guys. Perhaps these are differences from Algebra 1. We've got, as we're working with real data, the parameters of the linear model are important. So I have pulled from the first Chapter 8 video a scatter plot of verbal and math SAT scores for students, and I don't know how many students we pulled. It looks like we probably have well over 100 students here. This is from a problem in your textbook. We've got the linear regression model we know is in the form y hat equals mx plus b, or some of you guys have seen this in the book already. You'll see it as y hat equals b naught plus b1x. These mean the exact same things. They are just two different ways to represent the linear regression line. In the first, m is your slope, b is your y-intercept. In the second, b naught is your y-intercept, as it's not the coefficient for your x variable, and b1 is the slope, as it is the coefficient for your x variable. Well, again, because we're working with real units, those parameters of m and b take on special meaning that they may not have, at least for you guys when you were hitting your Algebra 1 classes, or in Algebra 2 when you review this concept early in the semester, early in the year. So, for instance, let's say that we have here, for this scatter plot, a slope that is equal to 0.7, okay? The slope can be represented, we know, as a fraction. We could put a denominator of 1 here. This means that for every, because our units are verbal SAT scores and math SAT scores, and we know that the slope is change in y over change in x, or change in math scores in this case over change in verbal scores, this means that for every 1 point increase or decrease in a student's verbal score, the model, the linear regression line, predicts that we're going to see a 0.7 point increase in the student's math score. Okay? Units are important. Make sure that you're breaking down how slope is being used in the context of each of these problems. Okay, so there's your slope. Y-intercept b. Something a little bit funny about this scatter plot, obviously, you can see very clearly from it, the verbal scores start at just below 300. So don't think that from any given scatter plot you can automatically just visually see what your y-intercept is here, okay? The y-intercept is not apparent from this scatter plot, as you can't see where the verbal scores are equal to 0. So the y-intercept is where our x values takes on a score of 0, or the verbal score would be 0 here. Let's say, for instance, that, just making this up, let's say that b was equal to 100. Again, because units are important, this y-intercept of 0 tells us that, well, the linear regression model predicts, hence that y hat here. We're not actually talking about what the y values are, we're talking about what this line predicts them to be. The linear regression model predicts a student would have a score of 100, a score of 100 for, on the math portion, for a verbal 0, not 100, for a verbal score of 0. Okay, so just as a short aside there, there's a refresher on what the linear regression model is and hopefully some further emphasis on the importance of the parameters that we're using with this thing. Okay, we're going to talk about next is a topic that doesn't come up a whole lot, but it's something to be important to be aware of, rather. We've got just some sample scatter plot here. I don't really care about what the numbers are. So any particular black dot is an x value and a y value. You've got your linear regression line running through this. One thing that we don't want to do with our linear regression line, and this is why you won't see me put arrows at the ends of these lines, we don't know that we can use this line past the x values we have. What do I mean by that? Well, it's not necessarily fair to assume that this line can make accurate predictions past that lowest x value that we have right here. Okay? And it's not necessarily fair to assume that our line can make predictions past the highest x value that we have right here. Not height. Highest. Okay? That's called extrapolation. Our regression line is, as long as we have met the three conditions that we talked about before. Quantitative condition, are the two variables both indeed quantitative, or is one masked as a quantitative variable when it's really categorical? Outlier condition and straight enough condition. If those three conditions are met, your linear regression model is going to be good just within the x values that you see in the data. You can't, for instance, say, let's say that we were predicting the gross domestic product in the United States for years in the past. It's not necessarily fair to assume that our regression line will be accurate for the future because, well, for one, you've got stock market crashes, you've got bubbles that collapse in the economy, that sort of a thing. But any sort of progress that you see within years of the past will not necessarily be the same progress that you see in the future. There's sort of a common sense example of why extrapolation is risky. So, when the book is asking you to determine, and the AP exam will do this too, I will probably throw a problem at you on the next test that's talking about well, it has extrapolation embedded in it. If you're being asked to make a prediction for what the model thinks some y value might be over here, for an x value you don't have, be careful about that. Think through whether or not that's fair. In almost all cases, that's not a fair use of the linear regression model. So again, extrapolation is risky. Be careful about it. Normally, that's going to be a sort of a trap question that's going to be thrown at you. Okay, the heart of this lesson is really with the residuals. We have talked about the importance of making sure that your scatter plot has at least an approximately linear form before you try to use the linear regression line to predict particular y values. Okay? Well, to analyze whether or not the linear form is there in the data, one of our tools is the residual. The residual is represented by lowercase e, and every one of these black dots, every one of these points on the scatter plot has a residual. The formula for calculating a residual is lowercase e equals y minus y hat. That means literally we are finding the difference. Let's look at this guy right here. It has an x value and it has some y value. Okay? The linear regression line for that particular x value right here predicts that the data would have a y value right here. Okay, so the regression line is clearly off from what the data is actually doing. The regression line says, well, for that same x value that you've got here and here, we think the y value should look like this, the y hat value that's a little bit higher. The residual says, okay, what's the difference between the actual data value and what the linear regression model predicts that data value will be. So for this particular case, because this is the difference of actual minus predicted, we have a negative residual here. This guy is negative. On the other hand, if you had calculated the residual for this guy right here, different x value, some y value, the regression line predicts for that same x value that you would have a predicted y value right in here. Okay, so I'm perhaps overusing my x's and y's here. Hopefully the color coding helps to keep things straight. So for that same x value, the regression line says, well, we think the y value is going to be a little bit lower. This guy right here, that's also a residual, the difference between your actual y right here and your predicted y, this time it's positive, okay? At a positive residual. The residual has, let me see if there's anything I want to say, also want to say on this. Okay, 2 roles of the residual. Let me write these out for you. 2 roles of the residual. Okay, first is this. Okay, it tells us how far off the model is. It tells us how far off the model was from the actual data, okay? The actual y value. That's the first thing, and that's pretty clear. Given that we're just subtracting the difference between y and y hat, I think that's absolutely clear. Any point on your scatter plot that is below your regression line has that a negative residual. Any point above your regression line will have a positive residual. And these are numbers. I'm just using E minus and E plus to stand in for whatever numbers we would get if we actually subtracted these differences off. Okay, so that's the first thing. It lets us know for particular data points how far off or how good a job the regression line actually did. The second thing here is that it allows us, when we look at all the residuals, it allows us to know about linearity. Okay, why do I say that? Well, in the next slide we're going to see how the calculator can actually give you the residual for every one of the points on its scatter plot. And we have a way that we can graph, we can make a residual graph that will allow us to basically take a magnifying glass to a scatter plot. And when we take this magnifying glass, we're going to be able to answer the question of whether or not the straight enough condition is met better than by just looking at the scatter plot of data itself. Okay, so let's look at that example. We've got, this is a problem that I pulled from the book. Classified ads in the Ithaca Journal offered several used Toyota Corollas for sale. Listed below are the ages of cars and the advertised prices. They want us to A, make a scatter plot for these data. We can do that. We've seen how to do that. First thing, make sure that you're aware of here is that you've got x values that sometimes have multiple associated y values. So you're being given multiple coordinate pairs, multiple points in your scatter plot for each, well, for some of the rows. For instance, for used cars that are 1 year old, you've got a y value here and here. So you would want to enter into your lists 1, 2 times. One of those ones would be associated with 12,995, the other with 10,950. Okay, so you've got, it's kind of an abbreviation. You've got multiple coordinate pairs in your scatter plot. All right, let me pull up Wabbit here real quick. I've got this data preloaded, and we'll make the scatter plot. Okay, we're going to back up because that's the plot that I'm trying to get to. I want to show you that the data is there. In column 1, you've got. Wait, what did it do? One 12,995. Okay, 2 is right. 3. Why is it duplicating? 4s are correct. There's the 10,950. Huh. Something weird happened here. I need to make a fix. We're going to delete that guy and delete that guy. So 1 is with my 12,995. So a 1-year-old car has its appropriate resale price. The other 1-year-old car has its appropriate resale price. 2's good. 3, 10,995, 10,995. 4, 6,995, and 79.90. Maybe it was just that one point that I made a mistake with. 5, we've got 8,700, 69.95. 6 is good. 9 is good. We've got all 3 coordinate pairs there. 11 has got its correct coordinate pairs, and 13 is good. Okay, so now it's up to speed. Okay, cool. All right, so we're going to make the scatter plot. We're going to go to second stat plot. We're going to, based upon what I've pre-set up, go to the second plot, turn that on. It shows the scatter plot. I input the explanatory variable in L1, response in L2, so we can zoom stat, dimension mismatch. So let's see, did I miss something? Did I still mess up my lists? That's good. Oh, I've got 2, okay, oops, I had 2 plots on. Second stat plot. Okay, so going back down to the second plot, we're good there. Now let's zoom stat one more time. And there you go. Okay, so we made the scatter plot. If you want, you can verify that all the data is there with your trace. We've got an X value of 1. That's a 1-year-old car selling for $12,995. And then it jumps to 2 only because I input this 1-year-old car that was selling for $10,950 at the end of the list. So if I go through all of the data here, it'll actually bounce back to 1 and $10,950. Okay, so we made the scatter plot. If we were to draw this on paper, we'd want to make sure that we had age on the explanatory axis, price advertised on the response. B, describe the association between age and price of a used Corolla. Well, the direction is clearly negative. We see as we increase in age, the price of the resale price for these cars go down. That conforms to expectations. That's good. So direction's negative. The form I would probably describe as approximately linear, but we do see a little bit of a curve in the data as we're going down this way. We're not following a linear trend. We do have some curvature here. That's something to look into, and the actual residual plot that we're going to make before we go into the next slide in these notes will help us to look at that form further. So that should raise a question for you. We're not following a great linear form, but it's pretty close. So I would describe this as approximately linear, but to note with a caveat here that there is a curve in the data. And then strength, moderately strong, I think is fair. Maybe describing this as strong. It's certainly not weak. The data are clustered fairly well. Okay, so do you think a linear model is appropriate? Well, let's look at that by doing the following. Let's go to second calc and go down to linreg. And linreg, we know, will give us, at the bare minimum, we know that it gives us the correlation coefficient based upon 2 variables of input. Well, I'm going to use it to do more than that. I'm going to use it to actually come up with the regression line, and also it's going to give me all the residuals for all those points we just saw in the last graph. So let's go second, or, well, I know my data is in L1 and L2, so go second L1, comma, second L2. For those of you who had the newer calculators, you would just input your X variable being L1, L2 would be your Y. We'll hit enter on that. And linreg here gave us a lot of information that we've not talked about. It gave us R, the correlation coefficient. We know that that's a pretty strong R. That tells us that the linear association does seem to be pretty strong, even though the form did have that curvature with the magnitude of R, the absolute value of this guy, being awfully close to 1. Y equals AX plus B. is the form they're giving us our linear regression model in. So actually, without calculating a whole bunch of stuff by hand, without going to 1var stats and getting the mean of all your ages and the mean of all your prices, you can actually say that the linear regression line that goes through this data has got to be y hat, let me alt tab, equals negative 924x, and then our b value was 12, 13, 31, 9.588. Okay, plus 12, 9.588. Okay, so that is your linear regression line. They gave you your a value, which was the coefficient for x, that must be your slope, the b value, which is a standalone constant there, at 12,319.588. So we've got the linear regression line from linreg. Well, that's cool. That'll save us some time. That means that we don't have to, for every new problem, calculate our slope based upon the correlation coefficient times the standard deviation of y over the standard deviation of x. We don't have to find the y-intercept by saying, well, it's got to be, we know the line runs through the mean of our x's and mean of y's. We don't have to do y bar minus m times x bar. All of that will only be necessary if you don't have the data, okay? So linreg will give us the linear regression line. That's the first thing I wanted to point out. Second thing here, even though it's hidden, if you go second list, scroll down to the bottom, there's this list here called resid. That's new. That is a list of the residuals for every one of these points in the scatter plot. Let me prove to you, or at least demonstrate to you, that that's the case. Okay, so I've got L1 and L2 right here. Let's go right here. Let me see if this will work. Second list, and I'm going to input resid. And L3 now is the residual, the difference between the actual y value and the predicted y value from the regression line for every one of those points. And if I scroll down, lo and behold, I've got the same number of entries in L3 as I do in L2 and L1 because every coordinate pair has a residual. All right, we can use this L3 here. This is how we're going to do this to make a residual plot. We're going to go second stat plot. We're going to turn the second plot off. We've already checked out the scatter plot. And we're going to go back to stat plot, turn the first plot on here. I've still chosen a scatter plot. Your x list is your x values from the scatter plot you just used. So L1 for me is the age for all these cars. I've input L1. My y list is no longer L2. Now I can go one of two routes. Because linreg stored all of the residuals in the resid list, I can use that. Or I could also, because I just said L3 is my resid list, I could use L3 instead. But I recommend that you just choose resid when you're trying to check out your residual scatter plot. Okay, so the mark is how the data shows up. That's fine. I like the squares. We'll go zoom stat, and there we go. Okay, so what we're checking out is the residual for every point we saw in our scatter plot. What you're looking for here when you're checking out whether or not, and this is a tool to use in answering whether or not we think the linear model is appropriate, if this is the residual for every point, like I said before, this is a magnifying glass on the scatter plot. Notice that we've got some curvature. Is that, oh, that's not going to show up. Darn it. We've got some curvature. Oh, there it goes. We've got some curvature in the residual plot here. Okay? Just like we said, we thought that we had, let me go back to the original scatter plot. Can I erase that guy? I can. Okay. Just like we had said that we thought maybe we had some curvature in the original scatter plot. Okay, let me turn the second scatter plot off. Or back on. I'll zoom stat. We said, oh, okay, well, it looks fairly linear, but there is some curvature here. Like I said, the residual scatter plot is a magnifying glass for the data. Okay? Notice how much clearer that curve is with my residual plot. Okay? Much clearer. So for every one of these points, let me trace across. We're told that that's got an x value of 1 and a y value of 1,599.4118. That's telling me, given that a residual is difference between actual y value for a particular point and the expected y value, or predicted y value, that's telling me that that first price for the one-year-old car was actually $1,599.4118 higher than our regression line predicted. If I scroll right here, for the 2-year-old car, the regression line was awfully close to the mark of $10,495. However, this 2-year-old car was advertised at $23.411765 higher than the regression line predicted. Okay, going across, same way here. Let's look at a negative one. For this first 4-year-old car, the advertised price was $6,995. Which was actually $1,628.588 less than what the regression line would have predicted. Okay, so again, we're just looking for a pattern in the scatter plot. Here, the pattern is clear in that we've got this curvature going on. When you see patterned residual plots like this, that is a fairly sure sign that the straight enough condition's not really being met. Okay, in this chapter, we don't have methods of dealing with the straight enough condition not being met very well. We can go one of two routes. We can say, when we're asked to make a linear regression line, we can either say, well, problem, you're asking us to make the linear regression line, and this is the issue that I have with it. I'm noticing in the residual plot that my data is not particularly straight, according to the residuals. And go ahead and make your your linear regression line to predict y values. Or you could say, well, if you've got a pattern trend that is really strong, you can just say, no, it's not appropriate to make, and see here, do you think a linear model is appropriate? No, it's not appropriate to make a linear regression line. We're seeing a patterned residuals plot, so we have to really stop there. Okay. Anything else I want to say on that? Okay, so yeah, let me recap here. There are two things you want to do. Two things to do in determining appropriateness of the regression line. Okay? The first is that you need to check out the scatter plot. Check out the scatter plot of the data. Okay? You need to make sure that the straight enough conditions being met from the scatter plot, you don't have any crazy outliers, etc., etc. Second thing, zoom in on data, on the data that you've got with your residual plot. And that's again done by putting the data into your lists, using linreg to get the residual list, and then making a residual plot like I just showed you. Okay, that's important. The residual plot is a big tool I expect you to use, especially when you're asked any question about the appropriateness of your model. All right, last thing we're going to look at here, let me check the time. 28, okay. Last thing we're going to look at is R squared. R squared is literally just the square of your correlation coefficient. Okay, linreg gives this to you. I'll erase that open parentheses. That probably looks confusing. And that gives me extra room here. Linreg gives this as a tool. Okay, now what does this thing mean? Well, check out the same sort of scatter plot that I've used the last couple of slides here. We've got 15 or so points. We've got our regression line throughout. And now I've introduced this dotted line here, which represents y bar, the mean of all your y values. Well, obviously, you knew this. Maybe you hadn't thought of this mathematically, but you knew this. You knew that for every one of these points in the scatter plot, you have some variation let's go just say varies. It varies from y bar. Every one of these points in the scatter plot varies from the mean of the y values. That's just kind of a duh. You guys have been like, yeah, of course. Not all the y values, for instance, not all the asking prices for these used cars would be the same. That's just silly. Okay. Again, we have variation from y bar. Well, statistically speaking, that variation, we're trying to explain how for any one of these x values that we give it, it could be a 1-year-old car, could be an 11-year-old car, a 13-year-old car, the regression line is trying to predict how a particular y value will look, how it will vary based upon the input of x that we give the linear regression line. Okay, so let's highlight this in blue. The variation that a regression line is explaining from y bar for this particular point down here, we've got this much, let's see how to write this, variation from y bar explained by the regression line. Okay? So in some sense, it's like the opposite of the residual. It's kind of telling us how, compared to that black bracket that I've highlighted for you, how good a job is the regression line actually doing in coming close to the actual y value. Okay? The rest of this variation from the regression line to the actual y value is variation from the mean of y explained by the residual. All right, let's just put E there. Okay? So for any particular point, for the second point that we highlighted up here, you've got, likewise, this is the amount of variation from the mean of y that is explained for that particular black point, highlighted right here. And that's the variation explained by the regression line. And then again in red, you've got this much variation from y bar explained by the residuals. And r squared, let me color code this a little bit better. If you added up all of those blue distances for all of these points and divided through by the difference between y bar and the actual y value, that would be r squared. It's the percent of the variation for all the y values that you see in your scatter plot that is explained by your regression line. That's worth writing out. So r squared is percent of all variation in y values explained by the regression line. Okay. R squared is a tool that will tell us how good a job, like I had talked about before, our regression line is doing. Let's go back, for instance, here to this data that we saw for these ages of cars and the asking prices that someone was trying to sell them for. Let me get this guy on real quick. Let's go to stat, calc, linreg one more time, and I will use the same data. I'm going to use L1, comma L2. So we've got year, asking price, and r squared is given to us here as 0.8937. That means that 89.37% of the variation in these asking prices that we see here in this table is explained by the regression line. That's pretty good. The regression line is doing an okay job of predicting what y values will be, versus if you see an r squared value of 0.1, that means that only 10% of the bouncing around in your y values, the variation in your y values from the mean of y, would be explained by a regression line. This is sort of just an introduction to r squared. R squared becomes more valuable in Chapter 10 when we start to do re-expressions of data to make a linear model fit when it wouldn't otherwise. So for now, what I would take away from these notes is that a residual is the difference between an actual y value and a predicted y value on your regression line. That's an important thing. You need to be able to make residuals plots. No ifs, ands, or buts about it. They will help you to identify the straight enough condition. Remember that your slope and y-intercept do have real-world meaning. It doesn't mean that the y-intercept and slope are actually true for the data. It doesn't mean that that's actually what the data is doing. It just means that that's what the